What if I told you that two particles, separated by light years, can instantly communicate? No, this isn't science fiction. It's one of the universe's most baffling secrets: quantum entanglement. Get ready to have your mind blown as we unravel the spooky action at a distance and explore how it defies everything we thought we knew about reality. Our story begins with the greatest mind of the 20th century, Albert Einstein. He gave us relativity, E=mc², and a new understanding of gravity, space, and time. But there was one aspect of the new quantum mechanics that deeply unsettled him. A theory he helped create seemed to produce a paradox so bizarre, so counterintuitive, that he famously dismissed it as spookhafte Fernwirkung, or spooky action at a distance. What made a mind that could comprehend the bending of space-time so uncomfortable? He was bothered by the idea that measuring a particle in one place could instantaneously affect another particle, even if that other particle was on the opposite side of the galaxy. To Einstein, this violated the universal speed limit, the speed of light. Nothing, he argued, could travel faster. This apparent paradox was at the heart of his lifelong debate with the other giant of quantum physics, Niels Bohr. To understand what spooked Einstein, let's forget the complex math and use a simple analogy. Imagine a special machine that produces pairs of quantum coins. It sends one coin to Alice in Kuala Lumpur and the other to Bob in New York. While the coins are in the air, they are in a state of quantum uncertainty, a superposition. They are neither heads nor tails. They are a fuzzy combination of both. But here's the rule: the coins are entangled. This means they are linked by a single, unbreakable property. In our case, the rule is that if one coin lands on heads, the other must land on tails. And if one is tails, the other must be heads. Their fates are interconnected. Alice catches her coin and looks at it. It's heads. At that very instant, she knows with 100% certainty that Bob's coin in New York is tails. The moment she observed her coin, the uncertainty collapsed for both of them. Now, you might be thinking, what's the big deal? Maybe the machine just sent a heads to Alice and a tails to Bob from the start. This was Einstein's argument, known as local realism. He believed the information was always there, like two socks from a pair put into two different boxes. If Alice opens her box and finds a left sock, she instantly knows Bob has the right sock. There's nothing spooky about that. The information, which sock was in which box, was predetermined. But here's the mind-bending truth that quantum mechanics insists upon, and that we've now proven: the coins, or particles, do not have a set state until one is measured. They are not a left and right sock from the start. They are in a fog of all possibilities. The act of Alice looking at her coin forced a reality into existence for both her coin and Bob's, instantly, across any distance. This is the core concept of quantum entanglement. It's a single, unified state shared by two or more particles. No matter how far apart they travel, they remain part of the same quantum story. One cannot be fully described without the other. Their fates are intertwined. For decades, the debate raged. Was it Einstein's hidden information, the socks in a box, or was it Bohr's instantaneous quantum connection? It seemed like a philosophical question, impossible to answer. Then, in the 1960s, a physicist from Northern Ireland named John Stuart Bell came along. He was about to turn this philosophical debate into a testable experiment. He devised a brilliant mathematical framework now known as Bell's theorem. The math is complex, but the idea is beautifully simple. Bell figured out a way to test if the socks in a box idea was true. He said, essentially, if the particles have predetermined properties, then when you measure them in lots of different ways and compare the results, your data will always follow a certain statistical pattern. This is called Bell's inequality. However, if the particles are truly spookily entangled as quantum mechanics predicts, then your measurements will produce a different statistical pattern, one that violates Bell's inequality. It was a direct challenge. The universe could be one way or the other. All that was left was to do the experiment. In the early 1980s, a team led by French physicist Alain Aspect did just that. They created pairs of entangled photons, particles of light, and sent them in opposite directions. They measured them again and again in clever, randomized ways. The results were stunning and unambiguous. Bell's inequality was violated, just as quantum mechanics predicted. Einstein, for all his genius, was wrong on this point. The universe is, in fact, spooky. But this leads to a huge and very common misconception. If the effect is instantaneous, does that mean we can use entanglement to send messages faster than the speed of light? Could Alice and Bob create an instant messaging device? The answer, disappointingly for sci-fi fans, is no. Here's why. Alice can't control the outcome of her measurement. When she measures her particle, she gets a random result, heads or tails, 50-50. She can't force it to be heads to send a 1 or tails to send a 0. All she does is measure a random outcome. She knows instantly what Bob's result will be, but that doesn't transmit any useful information. Bob also just gets a random result. The only way they know their results are correlated is if Bob calls Alice on a regular, light-speed limited phone and they compare their notes. The information about the correlation travels classically. Entanglement is a secret, private connection. It's a correlation, not communication. This all hinges on the very act of looking, known as the measurement problem. In the quantum world, you are never a passive observer. The moment you measure a quantum system, you fundamentally change it. Before you look, the particle is a wave of possibilities. When you look, you force it to pick one, a process called the collapse of the wave function. And when it picks, its entangled partner, wherever it is, picks the opposite. How this happens, the mechanism behind the collapse, remains one of the deepest mysteries in all of science. So, entanglement is real, but it's not for FTL communication. So what is it for? And what does it tell us about the universe? This is where we leave the realm of the proven and enter the world of mind-bending theories. One of the most popular interpretations of the measurement problem is the many worlds interpretation. This theory suggests that when you measure a particle, the universe splits. In one universe, Alice measures heads, and Bob's particle becomes tails. In another parallel universe that splits off at the moment of measurement, she measures tails, and Bob's becomes heads. Both outcomes happen, just in separate realities. In this view, entanglement is a bridge between these parallel worlds, ensuring that the laws of physics remain consistent across all branches. It's a wild idea, but one that many physicists take seriously. But entanglement isn't just theoretical. It's at the heart of a technological revolution, quantum computing. Your classical computer works with bits, which can be either a 0 or a 1. A quantum computer uses qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. Now imagine you have 2 qubits. Classically, you could have 4 possible states, 0, 0, 0, 1, 10, or 11. Your computer can only work with one of these at a time, but 2 quantum qubits can be all 4 of those states simultaneously. Now, what happens when you entangle hundreds or thousands of these qubits? The number of states they can explore simultaneously becomes astronomical, larger than the number of atoms in the known universe. By entangling qubits, a quantum computer can perform a massive number of calculations in parallel. It's like being able to check every book in a library at the same time, instead of reading them one by one. This power could help us discover new medicines, create new materials, and solve problems that are currently impossible for even the fastest supercomputers. Ultimately, entanglement forces us to ask a fundamental question: what is reality? It suggests that the universe is not a collection of separate objects, but a deeply interconnected whole. The concept of distance, of separation, might be an illusion. Two particles light years apart are, in a quantum sense, still touching. This idea, known as non-locality, challenges our most basic understanding of space and time. It hints that there may be a deeper hidden layer to reality that we are only just beginning to perceive. The future powered by entanglement is already being built. One of the most exciting applications is the quantum internet. Traditional encryption relies on complex math problems. A powerful enough computer, especially a quantum computer, could one day break it. But communication based on entanglement is, in theory, unhackable. Imagine Alice and Bob share a stream of entangled particles. They use their measurements to generate a secret key for encryption. If an eavesdropper, Eve, tries to intercept and measure one of the particles in transit, the very act of her measurement will instantly break the entanglement. Alice and Bob will see that the correlation in their results is gone and will know the line is compromised. It's a security system enforced by the fundamental laws of physics. The applications go beyond computing and communication. Quantum sensing uses the extreme sensitivity of entangled states to measure things with unprecedented precision. Entangled photons could lead to medical imaging that can see individual biological processes inside a cell. It could create clocks so precise they wouldn't lose a second over the entire age of the universe. They could allow us to build cameras that can see around corners or detect submarines deep in the ocean by measuring tiny gravitational fluctuations. But despite all we know, entanglement still holds deep mysteries. Perhaps the biggest unanswered question is how it fits with Einstein's other great theory, general relativity. How does entanglement work with gravity? Some physicists, following a tantalizing idea called ER equals EPR, speculate that entanglement might be intimately connected to wormholes, shortcuts through spacetime. The idea is that every pair of entangled particles might be linked by a microscopic wormhole. This remains highly speculative, but it shows just how deep our quest to understand this phenomenon goes. The world of quantum physics can seem intimidating, but you don't need a PhD to appreciate its wonder. There are incredible books, documentaries, and online courses that can take you deeper into this world. The journey begins with a single question, a moment of curiosity. The story of entanglement, from Einstein's skepticism to the race to build a quantum computer, is a fundamentally human one. It's a story about our relentless drive to understand the universe, to ask why, and to push the boundaries of what we believe is possible. It reminds us that even our most deeply held intuitions about reality can be overturned by careful observation and bold new ideas. We began with a mystery that seemed like a paradox. We end with a proven reality that is powering a new technological frontier. Quantum entanglement shows us that the universe is not just stranger than we imagine. It's stranger than we can imagine. And it reveals a profound truth. At the most fundamental level, everything is connected.